Thank you so much. It's a great pleasure to be back at Humboldt. It's a great pleasure to have so many distinguished people in this group and such a diverse set of distinguished people in this group. So I'm not going to talk about volatility today. I'm not going to talk about weather derivatives. I'm going to talk about something totally different. I'm going to talk about, well, I say totally different. It's actually very much related. I'm going to talk about yield curve modeling. Okay? So I made these slides in a way that hopefully will do the trick. This is a diverse audience, so I've made them kind of broad, yet hopefully there's enough in there such that the aficionados will feel satisfied as well. And there are lots of issues running through this. We're supposed to be doing a book on this now, so we're thinking about lots of sorts of issues. Initially, I promised Wolfgang a title along the lines of 200 Years of Yield Curve Modeling. I very quickly withdrew from that heroic task, in part because of my own lack of knowledge of history, in part because in some sense yield curve modeling began with Vasicek in 1979. So my old friend Dan Nelson, who many of you know used to work in volatility, passed away a few years ago. I once heard give a literature review. He was talking about derivatives and derivatives modeling, and his literature review was, first the earth cooled, and then finance formed, and then Merton wrote his 1974 paper. So it's sort of like that in yield curve modeling with Vasicek. But I want to come back to that and talk about various issues as we go. But let's get into it, and then at the end I'd like to look both retrospectively and perhaps more interestingly from a research point of view, prospectively in terms of where are things going. But there are lots of issues here. We might want to go parametric, we might want to go non-parametric. We might want to work under risk neutrality, we might want to work under risk aversion. We might want to allow for arbitrage opportunities, or we might want to insist that they're impossible. We might want to entertain stochastic volatility, or we might not need to. We might want to incorporate nonlinearities, or maybe not. We could go on and on with those sorts of things. And the literature involves different people at different times going in various ways. So I'm going to show you how we being my group at the University of Pennsylvania, have been proceeding for the last few years, or it's more than a few years now. It's probably 10 years since we started all this. And there's lots of different aspects of this literature branching out in different directions now. I'm going to tell you about some of them and what we find exciting. So let's see, there we go. All right, now I'm well aware that starting a talk by listing a bunch of your own papers, you know, invites derision. You know, you're probably thinking, my God, this guy is an egomaniac. He has to list, you know, blah, blah, blah. It's not like that. I am indeed not an egomaniac, I promise you. However, what I want to do here is situate this talk and where I want to go ultimately in this talk, which is what's in yellow, the more recent work, in broader context. All right. So I also want to mention the names of people whose names should be mentioned. You notice I didn't put any names there. My name's on all these things, but there are plenty of others. So this research that I'm going to show you started with Kan-Lin Lee at the top there, a student of mine who's now at UC Riverside. And, you know, in that we sort of worked out what I'm going to call a dynamic Nelson-Siegel model. We'll look at that in some detail in just a minute. So I won't try to sketch it right now, but it's a particular dynamic model for term structures of bond yields. and it's one that has some appealing properties, as I'll argue. And then in subsequent work with Baran Aroba up there, who's now at the University of Maryland, a former student who's at Maryland, and Glenn Rudebush, who's at the Federal Reserve Bank of San Francisco, we try to bring in covariance. In particular, as the yield curve moves over time, it's not just moving for random reasons, right? It's moving presumably, or at least in part, due to underlying movements in macroeconomic fundamentals, inflation expectations, the business cycle and real activity, volatility through convexity sorts of arguments, and so on. So we can think of macro fundamentals, dare I say, causing movements in the yield curve, and conversely. You know, there's feedback, right? The yield curve has a lot of predictive, forward-looking aspects to it. It might serve as a leading indicator for things like real activity as well. So that's what we're doing up there with Rudebush and Aroba. Then in another paper, the third one there with Lee and Vivian Yua, who's now at NYU, we brought in global aspects. The dynamic Nelson-Siegel model, as you'll see in a minute, is a factor model. It's a certain kind of dynamic factor model in which country yields load off of country factors. But in a global context, you can go farther and make this hierarchical. We can have country yields loading off of country factors, but country factors may load off of regional factors, and regional factors may load off of global factors. It's not guaranteed, but that's a testable hypothesis. But at any rate, that's the route we take, which takes us toward global yield modeling in the work with Lee and Yua. And then in the last three things, and especially the ones in yellow, we started to deal with this arbitrage issue. How do we think about arbitrage or no arbitrage? You know, if you're a finance person, doing anything in an environment that admits arbitrage is just completely sinful, okay? On the other hand, from a predictive point of view, I don't care. If I can predict bond yields better than the competition, in part my view is I'm going to be a hero, and if I do that in a way that happens to admit arbitrage, so what? And moreover, when you think about it, absence of arbitrage is basically equivalent, in fact it's precisely equivalent, to absolutely perfect markets. And it's just not obvious to me why I should insist always and everywhere to work under assumptions of absolutely perfect markets. We'll have more to say about that. At any rate, in work with Monica Piazzesi, who was at Chicago at the time, wait, where is she now? She's at Stanford now. Now she's at Stanford. And Rudebush, we started thinking about those sorts of issues. And then there's this guy, Jens Christensen, who comes in at the bottom, you can see there. He's great. He's a young guy at the Federal Reserve Bank of San Francisco, a student of David Lando's from Copenhagen, and he knows everything. So we just try to keep up with Christensen. It's not always easy. So here's what we're going to be doing. Or here's a picture that's related to the things we're going to be doing. These are four time series of yield curves. So it's an interesting modeling situation. It's a kind of functional situation, right? The object on which we have time series that are plotted here are yield curves. So at any point in time, you have a curve, okay? The curves here, if you're not used to working in bond markets, these are called yield curves. They give the yields, in these cases on government bonds, as a function of maturity, measured in months. So going clockwise, say from upper left, we've got US, Germany, UK, and Japan. And you know, as you go kind of rightward on any one of those axes, that's going over time from the mid-80s, more or less to the present. As you go kind of up and to the left, you're going across maturities, okay, from 3 months through 120 months, 10 years. In this picture, In these slides, I'm actually blending stuff from different papers, and as time has gone on, of course, the samples that we can get have grown. So there's a little bit of lack of coherence across the slides. So in some slides, we'll take maturities past 10 years. We'll actually go out to 30 years. But at any rate, so you can see these are just examples of yield curves. So the ultimate object to be modeled is a three-dimensional surface, right? So it's kind of interesting and tricky. And of course, these surfaces do lots of things. They float up and down. They twist around. The curvature may change. And you know, you can see things that you think you should be seeing. You might look at Japan, for example. In recent years, you see the yields are all near zero. You know, Japan has had some rough years and so on. But you know, there's lots of movement in these curves, and it's not at all the case, for example, that as yield curve shifts, they're just parallel movements or anything like that. There's lots of action potentially in there to be modeled. So what's here, what I'm going to, let's think about this literature. When we started thinking about this some years ago, you know, let me just back up for a second. I'm going to approach this from a predictive point of view, okay? You know, I take it as self-evident, and I don't think I'll have too much problem convincing this audience that it's self-evident that it's of interest to think about predictive modeling of something like bond yields. It's just intrinsically interesting to statistically oriented people like us, but also in the financial markets, of course, in terms of asset allocation and trading strategies, that's immediately and obviously relevant. Also, the flip side of that is risk management. If you want to do risk management, you know, hedge risk associated with different sorts of bond portfolios, it's crucially important to model the dynamics of the, you need to know what you're hedging, what you're trying to hedge. Also for pricing any, you know, fixed income kind of asset, that's what the yield curve gives you. It tells you what the price should be. So whether you're doing asset allocation or risk management or pricing, you know, that's where we are. But I'm going to focus more on predictive issues. So when we started thinking about this, we started thinking about prediction, and you know, here's a partition of the literature. It's a horribly crude partition of the literature, kind of into two parts, but I think it's actually correct and telling. You know, part of the literature has what I'm calling up there a cross-sectional flavor. One classic paper being Heath, Jarrow, Morton, HJM. And there are many, many papers in that tradition. But it's all about pricing bonds perfectly at a point in time, okay, and in a way that's free from arbitrage, which is very important if you're a trader, and it's actually deservedly a tremendously classic contribution, and that literature is very important. But it's not predictive by construction. It's about the cross-section of bond yields. It's about something that occurs at a point in time. So that's fine, but it's not going to take me where I want to go. The second part of the literature, if you will, which traces to Vasicek, is very explicitly dynamic. One starts with a dynamic model for short rates and then figures out how long rates must behave or cohere to eliminate arbitrage possibilities. And one can use those models for prediction. You know, there's an underlying time series process. It turns out, though, people have begun to realize in the last 5 years or so, with precision, that those models actually predict very, very poorly. In fact, there's a famous paper by Greg Duffy in the Journal of Finance devoted to exactly that issue, makes the case very clearly. It turns out that the affine models that used going back to Vasicek and then through Duffy, Darrell Duffy, the other Duffy at Stanford, and Singleton and many others, impose certain restrictions that are just violated by the data, and that winds up really hurting predictive performance. It's not been clear how to get away from those restrictions while maintaining tractability. So there are issues, but at any rate, in terms of this partition of the literature, you know, there's part of it's cross-sectional in flavor. It doesn't help us. Part of it is dynamic and useful potentially for prediction, but it turns out to do very poorly. So we're just kind of stuck. And You know, actually, honestly, I don't remember how we got exactly going in this, but we were sitting around one day, I'm sure, you know, just thinking about this, and somehow I knew about Nelson Siegel. Nelson Siegel's an old classic yield curve model, and very tightly parsimonious, which usually is a good thing in predictive environments, other things equal, anyway. But another one of these cross-sectional models. It's, you know, very popular in industry, in central banks, in certain corners of academic work. But it's another one of these cross-sectional models. It's basically just a arguably flexible functional form for fitting a cross-section of bond yields. But when you look at it, you can see very quickly how it could be dynamized, and it's going to turn. And you know, so that's what we did. And you can see very easily how it has a state-space structure and really blast off. So that's where we're going to go. That's what we've done, and that's where we're going to go. So I'm going to take this model. I'm going to take this model called a Nelson-Siegel model, and I'm going to first of all show you that it has a modern interpretation. It turns out to be, when you dynamize it, it's a dynamic factor model, where moreover, those three factors, it's a three-factor model, are provably level, slope, and curvature. Just like the way I started talking when we looked at those pictures of yield curves. Some things like inflation should be linked to level shifts. Other things like real activity, for economic reasons, you'd expect to be linked to slope, and so on. Well, the factors in this model turn out to be level, slope, and curvature. I'm going to show you some aspects of its flexibility and how it fits, and ultimately, of course, how it forecasts. And there are many variations, extensions. I'll show you some of them. And we'll think about this arbitrage issue. And I think that's the key issue moving forward. Do we care or not care about imposing no arbitrage? And what does the performance look like depending on what we do? All right, so here's some notation and so forth. I understand it's late. This is going to be a very simple talk, you know, but this is just notation. So, you know, you can work with a discount function or a forward rate curve or a yield curve. Those are the three things written there. The discount function up top just gives the value of you know, a euro received tau periods in the future. Okay, so you're discounting it back to the present. So tau, though, mostly this slide is just notation. So in moving forward, tau is going to be maturity, measured in months. Forward rates, F would be in the middle panel, and then yield curve at the bottom. These are the standard formulas relating them. So notice, for example, in the third formula, if I know the forward rate curve, I can just integrate it appropriately and get out the yields. Or if I know the yields, I can just take them up top and get out the bond prices from the discount function. Or if I know the price is P, I can do the middle thing and get the forward rates. You know, so you can work in whichever environment you want. Most, not all, but most people, including myself, are a little more comfortable working with yield, so we're going to work with yield curves, but you know, it doesn't matter. So Y is for yield, T is for mature, or tau, Greek letter tau is for maturity. T, of course, is going to denote a time period. So here's the Nelson-Siegel curve. Okay, so the Nelson-Siegel curve, as introduced by Nelson-Siegel, again, is a static model. It's a flexible functional form for fitting a set of yields at a point in time. So the yields at maturity tau, this is all at the same point in time. So there's no time subscripts going on here. Yields at maturity tau are assumed. You can go back and look at the Nelson-Siegel paper to see where this comes from. It looks sort of like the solution to a differential equation in some sense, where there are a lot of exponentials floating around. And it actually is linked to that. And it also imposes some things that are desirable from a financial point of view, like the discount function. The value of a euro as a function of maturity must go to 0 as maturity goes to infinity. And so things that from a financial point of view, you know, must hold. It's not the only functional form that has those properties, but it's arguably quite appealing, and it's gotten very popular. So this is what it is. But Nelson-Siegel motivate this, you know, as a cross-sectional curve fitting sort of tool. So in this kind of environment, the parameters of this curve would be beta 1, beta 2, and beta 3. There's another parameter in there, lambda. But if you get into this, you'll see that lambda you can usually pin down a priori, or just fix it. So if lambda's fixed, then this is just a linear regression, right? You're just regressing in the cross-section, you're regressing yields on an intercept, and some strange variable, 1 minus e to the negative lambda tau over lambda tau, and some other strange variable, e to the negative lambda tau. But if you know lambda, those are just variables, so you can just run it as a linear regression and read off these parameters. And you do that, and people have done this, and the Federal Reserve Board in the US actually puts these Nelson-Siegel curves on the web every day, and it's a big deal, if you're into this kind of stuff. The Nelson-Siegel tends to fit well, and so on. I'll show you some aspects of that in a second. Well, here's a typical day, okay? This is some day in 1997. I'm just showing you one day, but it's absolutely typical. The actual yields are the asterisks there, and the fitted curve is the Nelson-Siegel curve. It turns out if you play around with Nelson-Siegel, you can see that the Nelson-Siegel curve can be, linear, or it can be increasing at an increasing or decreasing rate, or decreasing at an increasing or decreasing rate, or U-shaped, or upside down U-shaped. It's fairly flexible. The only thing you can't get is a wiggle, like more than one internal optimum. But yield curves hardly ever have that. They're typically very, very smooth. Not linear, but very smooth, like this. This is a very typical day. So of course the points that correspond to the observed yields on this day are not exactly on the line. People who insist on no arbitrage would get upset by the fact that the points aren't exactly on the line. They'd want to price these bonds exactly. My point of view as a predictive econometrician is I'd probably get more upset if they were on the line. I'd be very suspicious of, in-sample overfitting. At any rate, so here's, let's start to dynamize this thing. What's written at the top is the same Nelson-Siegel model. I just factored it differently. It turns out to be more productive for where I want to go to do that. But it's the same model that we just looked at. So as you go from the top line there to the second line, you notice what's happened. First of all, instead of writing beta 1, 2, and 3, I've written L, S, and C for level, slope, and curvature. It's going to turn out that that's what they are, okay? And notice I have time subscripts on the lower thing as well, because this is going to be a dynamic model now. So the lower equation there says that the yield curve at time t, has that form. But notice that the parameters that used to be called beta 1, 2, and 3 are now level, slope, and curvature, and they have time subscripts on them. So we're going to completely kind of invert the interpretation of the model here. Instead of thinking of the betas up top as parameters and the other stuff multiplying them as variables, we're going to think of the L, S, and C down at the bottom there as variables. They're going to be moving around. And the stuff multiplying them are going to be parameters. They're going to be factor loadings, in other words. So L, S, and C down at the bottom there, you're going to think of time-varying factors, latent factors. And the things multiplying them, the strange functions of, the strange exponential type functions, are going to be factor loadings. Okay? So this is going to be a dynamic factor model, a three-factor model. It's not obvious yet, unless you're a lot smarter than I am, why those things that I'm calling L, S, and C really are level, slope, and curvature interpreted factors. But at any rate, it's obvious that it has a dynamic factor structure. All we have to do is put lay some dynamics on L, S, and C, and you can see it's a state space system immediately. This would be the measurement equation. Okay, and then we need some dynamics on those factors. That would be the transition equation, and then we can blast off with all sorts of stuff. But let me show you, before we do that, let me show you something here. If you just plot out, what's the factor loading on the level? It's just 1, of course, so it's fixed at all maturities. And then there's the non-degenerate loading on slope and a different one on curvature. If I plot them out as a function of maturity for any value of lambda, qualitatively they'll be the same. They look like this. So the factor loading the first factor loading on the first factor, beta 1, is just 1 at all maturities. That's the thing at the top. Okay, enough said. But you see that's how you know it's a level factor, right? So suppose beta 1 goes up or something. What's going to happen to yields? All yields are going to go up by the same amount because they all load on beta 1 with a unit loading. So immediately you can see that beta 1, as it moves around, it causes level shifts in the curve. Differently, you have there the loading structure on the second factor, on beta 2. It's monotonically decreasing. So imagine, say, that beta 2 goes up for some reason. What's going to happen to yields? Well, the short yields are going to go up by a lot because they load heavily on beta 2. But the long yields are hardly going to move at all because they don't load much at all. So that's going to change the slope. Right? And then finally, the loading on beta 3 has this home-shaped structure. So as beta 3 moves, what's going to happen? The shortest yields won't move much because they don't load much on it, and the longest yields won't move much because they don't load much on it, but the middle yields will. So that changes the curvature. So you can see, and you can prove this much more rigorously than by talking through a graph, but intuitively, this graph, I think, says it all. You can see that these are level slope and curvature factors. Okay? So now we're at this place where you can see what's going on. So writing this out in more traditional kind of state space, so here on the left, we've got, this is all at time t. We've got the yields at all the different maturities. Then we've got this big measurement, system matrix with all those lambdas in it. Multiplying the underlying factors, which we've now shown are level slope and curvature. And then, of course, we've got idiosyncratic noise as well. That's what those epsilons are. So we've arrived at this model, which is a state space model. And, if we write it in a more concise notation, we get what's up top there. And where I've now put some dynamics on the factor, the vector of factors, F would just be a vector containing the level, slope, and curvature. So with no loss of generality, we can just write it as first order dynamics. So there you have, precisely a very standard state space representation of this setup. So you start with this simple little Nelson-Siegel curve for the cross section, but very quickly you can dynamize it. It's a nice tidy state space system where, moreover, the state vector contains these level, slope, and curvature components. So for all the things we want to do, of course, it's convenient to notice that it's a nice, in fact, it's a linear state space system, and if I'm willing to assume normality, it's a linear Gaussian state space system. But at any rate, for all the things we want to do, it's nice to be aware of the state space structure. I'm going to want to do things like extract the unobservable level, slope, and curvature factors, optimally in some sense, like, in a least squares sense. Of course, the Kalman filter will give me that. I'm going to be interested in predicting those level, slope, and curvature factors. Because notice what's going on here. Notice what we've done, right, is we've distilled the yield curve. What this model does is it distills the yield curve into just three objects: level, slope, and curvature. Right? If you give me level, slope, and curvature, I can just plug them into the Nelson-Siegel curve and crank out the whole yield curve at any maturity. So in particular, forecasting the yield curve in this environment just amounts to forecasting the state vector, level, slope, and curvature. If once I project them, I just plug them into the curve and I have my projection of the whole curve. So I'm not just going to want to extract level, slope, and curvature. That's of interest from a historical learning about the data point of view. But also I'm going to want to predict. And of course the Kalman filter will do that as well. And last but not at all least, I'm going to need to estimate. And through a prediction error decomposition, the Kalman filter will also let me do exact maximum likelihood, which is feasible. I mean, this is a very low dimensional, parametric model. So, so at least in principle, in terms of organizing your thoughts about this problem, the state space perspective is very helpful. In practice, I don't think it's a big deal. We sometimes actually do it directly in state space. Sometimes we do this two-step procedure that I'll tell you about. All right, so let me tell you right now. So you all know the Kalman filter and so on, and so immediately we could estimate this model by maximum likelihood. And it is tightly parsimonious and all that, but you still have a lot of, you still have, like, the dimension of the y vector there is equal to the number of observed yields. that you have, which might be 10 or 15 or 20 or 25, you know, so which is to say the dimension of the covariance matrix of epsilon is also, you know, 15 or 20 or 25. So it's not trivial, you know, I mean, you know, you start, even if you pare it down a lot, you're still trying to, you know, doing numerical iteration and on 20 or 30 or 50 or 80 parameters, you know, that's far from trivial. It turns out there's a much simpler two-step procedure. It's a two-step as opposed to a one-step, so there are some issues, some statistical issues. But in any case that we've ever seen, when we can get the one-step MLE to converge in a credible way, it matches the two-step. And moreover, there are lots of times we can't get the one-step MLE to converge, so there's no choice but to do the two-step. But any way we can see it, it matches. I mean, not exactly, not numerically identically, but for all practical purposes. The two-step, of course, would be the following. At any point in time, you've got a cross-section of yields, right? So you fit Nelson-Siegel. You do that every day. After a while, you've been doing it for hundreds of days. So you've got a time series of the fitted Nelson-Siegel parameter, just a three-dimensional time series, and then just go fit a vector autoregression or something to them, right? And that's what the state space model is all about. It's just doing it in one step, but you can split it up. You estimate the curve day by day, and then estimate the dynamics associated with the evolution of the factors that govern the curve. All right. So anyway. All right, so if you look at these papers that we started with, you can see lots of details in this. I'm just going to show you a few things that are illustrative and typical. So again, forecasting in this environment, forecasting yields just boils down to forecasting the factors. So there are lots of things one can do, of course, in terms of the dynamics you allow on the factors. In fact, after a little experimentation, but also before we experimented at all, we were just led to univariate thinking. The idea being the following. These factors, level, slope, and curvature, are of course they're not the principal components, but they're also not far from them. I don't have a slide on that here, but you can compare them, and you know, they're reasonably highly correlated. In fact, quite highly correlated. And the principal components, of course, are orthogonal by construction, so you would expect that these factors, although not orthogonal, are perhaps, you know, approximately orthogonal, and sure enough, they're quite close. So even though in general, in the state space kind of model like this, there's no reason why that A matrix in the middle there's no reason why that A matrix should be diagonal, and there's no reason why that sigma matrix should be diagonal. In practice, and I think it's linked to this closeness to the principal components, in practice that's actually not doing damage at all to the data, and and if you can impose a restriction like that, you know, it tightens up the parameterization nicely. So we almost always, in fact always, work with just a stacked set of univariate AR1s, in fact, for our dynamics, just as written there. So you could get fancier, of course, and there's nothing magical about an AR1. That's much less tied down. But the orthogonality or near orthogonality, I actually feel quite strongly about. It's helpful to be aware of that and not try to estimate all sorts of multivariate interactions that ultimately are really not there. So here's how things tend to work out. Again, this is just one particular slide. You can find dozens of these much more extensive examinations in the paper, but qualitatively they're all like this. And these kind of slides are going to come a fair amount, so I want to spend a little time just making sure we know how to read this, okay? So what's shown here, we're looking at the predictive performance of this dynamic Nelson-Siegel relative to a benchmark. The benchmark here happens to be no change, which is to say the optimal forecast that would correspond to random walk or martingale behavior. We're going to look 1 month ahead, 6 months ahead, and 12 months ahead. These are actual out-of-sample forecasts. Okay, so depending on the paper, we just estimate and freeze the estimates and then start predicting out of sample, or sometimes we get fancier and actually recursively update the estimates as we go through time. But in any event, they're always what could have and would have really been done in real time, and there's no, look-ahead bias or anything like that. So at any rate, so we're doing 1 month, 6 month, and 12 month ahead, out of sample prediction. We're going to score how we do relative to a random walk in this case. So the 3 panels correspond to 1, 6, and 12 months ahead. Now take any given panel, like the one on the left, for 1 month ahead out of sample prediction. It's got a bunch of dots and a horizontal line and so on. What's on the horizontal axis is the maturity of the bond yield. We can look at 1 month ahead forecast. What are we talking about? 1 month ahead forecast of the 10-year rate or the 1-year rate or the 20-year rate? That's the maturity that's on the horizontal axis. And then what's on the vertical axis is this comparative predictive performance. Where, for better or worse, we could look at other loss functions, but we're looking at quadratic loss here. So this is root mean squared error of us relative to root mean squared error of the random walk. So if that ratio is less than 1, we're doing better. If it's not, we're not. So that's why that horizontal line is drawn in each case at 1, just for visual reference. So what do you notice when you look at this? Look at the left panel, for example. 1 month ahead forecasting. Notice that we're not doing any better than a random walk, right? Sometimes we do a tiny bit better. Sometimes we do a tiny bit worse. But of course, these are sample root mean squared errors. There's sampling uncertainty on them. If we did a formal test of significance of difference in predictive accuracy, and in fact we have, they're not shown in this graph, but those different. Nothing in that left panel is statistically significantly different from 1. So it looks pretty depressing, right? But the interesting thing is that as you move rightward, that you can see, whoops, tangled up here. You can see that things change. Take the middle panel, 6 months ahead. Systematically and statistically significantly, it turns out, those points are less than 1. Go to the rightmost panel, which is a year ahead. It's a pretty big deal, right? You're talking about significant reductions in out of sample root mean squared error relative to the random walk. Well, let me say a few things. Just trying to think of where to start. First of all, go back to the left panel for a second. Looks pretty depressing. Maybe it is, But I would argue, I think it's definitely true, that inability to dominate the random walk is actually exactly what you'd expect for short horizon forecasts. Because the yield curve is a very highly persistent dynamic. It evolves with very highly persistent dynamics. Is it exactly a martingale? Who knows? But at any rate, the dynamics are very highly persistent. Just imagine that I asked you to predict the yield curve for 5 seconds from now. What would be a great forecast? The current yield curve. Nothing would beat it. Right? And now, the shortest horizon there is a month. That's a lot longer than 5 seconds, but it's not that far out. Right? The yield curve dynamics are very highly persistent. It's not bouncing around from week to week or month to month, very much. So it's at medium and long horizons, though, where you'd expect the eventual mean reversion that perhaps our model is capturing to have a chance to shine, right? And you can see, and that's what happens, right? As you move rightward, and this happens no matter what you do. Again, this is just one particular case, but it's typically about 9 months out, let's say 6 to 12 months out, where we get maximal action. At the shortest horizon, you're just not going to beat a random walk. At a long horizon, 10 years or something, nothing's any good. Who knows what's going to be happening in 10 years. But at this interesting mid-horizon of 6 to 12 months, which actually corresponds to a lot of the horizons of interest in finance, for asset allocation, risk management, and so on. 2 to 4 quarters, that kind of thing. You see a lot of action there. It's not the same across all maturities. Most of our action tends to be at the shortest maturities. The long maturity there, 10 years, we get a little improvement, but not as much. We'll come back to that. That's going to be important, actually. All right? Okay, so that's just sort of some background and how the framework works. Let's kind of zoom in on this arbitrage issue, okay? Because that's a big deal in finance. I mean, that's a huge deal. And it really has a lot to do with where I think this literature is going, or will go. So, Roman numeral 1 and Roman numeral 2 are two perspectives. It turns out they take you to exactly the same place. But it's worth thinking about the two perspectives for a second. Perspective 1, Roman numeral 1, is how we came upon things historically, sort of how we're thinking. Dynamizing Nelson Siegel. It's about dynamic Nelson Siegel. And you do that, and you do all the things that we just spent the last 45 minutes talking about. And you feel good about yourself most of the time. But every once in a while, you know, you wake up at 3 a.m. and think, you know, I really should figure out about maybe how to impose no arbitrage in this world because, you know, I just should, okay? By the way, I didn't mention it, but Nelson Siegel, including its dynamic version, is provably not free from arbitrage. Okay? Now, just to elaborate slightly on something I mentioned before, for a lot of purposes, and still to a good degree, I think, that doesn't bother me. I mean, again, if I can do good predictions and do better than anyone else the things we want to do, who cares if it admits arbitrage? And maybe if somebody could figure out how to make it arbitrage free, maybe they could do even better, who knows? But at any rate, if I could do some good things, I can do some good things. But still, you wake up at 3 a.m. sometimes, you know, thinking about that. For good reason. I mean, you know, finance guys, it's not silly to worry about arbitrage opportunities and why they should, in general, not exist, and so on. But the point is, there's another point, and it's this. You know Nelson Siegel fits well. I haven't shown you everything at all, but you know, I've shown you enough that you can probably see it actually fits very well. Therefore, if the real markets are free from arbitrage, my dynamic Nelson Siegel must at least be approximately free from arbitrage because they fit well. And conversely, if the real markets have important arbitrage opportunities, well then why would I want to force the absence of them in my fitted model? So anyway you slice it, it seems like I'm okay. But still you wake up at 3 a.m. Okay. But anyway, that's the root. Roman numeral number 1 is kind of coming with Nelson Siegel and eventually saying, hey, I didn't think about no arbitrage. Could I and should I make it free from arbitrage? Okay, so that's the first root. The second root there oh, I'm sorry, let me just say one more thing. Or let me summarize the first root from a certain point of view. So the thing about the first root is, it's trivially easy statistically, you know, the calculations here are just Kalman filtering, or for that matter, really just, you know, linear regressions. I mean, this is as trivial and as numerically stable, you know, as you're ever going to be. So from a tractability point of view, it's just wonderful. From a pure theory point of view, there are issues. It admits arbitrage possibilities, and finance theorists don't like that. Okay? So from a practical perspective, it's kind of great. From a theoretical perspective, maybe not. Now, come to number 2. There's this big literature that goes back to Vasicek through Duffy and Kahn and Dye and Singleton and hundreds of others. Very distinguished, very important literature. It tends to, it makes use of affine models. We'll write down some affine models in a minute. And, you know, works out how yield curves should look. So that literature has exactly the opposite set of pros and cons. It's very elegant theoretically and forces absence of arbitrage, but unfortunately, as is now well known, it's highly intractable. These models are highly intractable in terms of fitting to data. They're very highly parameterized. The likelihood or other objective functions have numerous local optima, to put it gently. I mean, you'll actually, in the more honest papers in this literature, you'll find paragraphs like, you know, we played around for a few hours with initial conditions and we let it run overnight and things weren't looking good, so we coaxed it this way and that way, and after a few days we just stopped, but things look okay. You know, I mean, that's actually almost a paragraph from one of Greg Duffy's papers. So it's really an issue. You know, these affine and related arbitrage-free models are great theoretically, but you don't see them applied that much in practice, and it's no accident. They're not tractable. So you get just the opposite set of attributes. But again, you can get to the same place either way. You start with the nice theory models. You want to say, gee, how can I make them tractable? Or you start up top with the nice tractable models, and you want to say, gee, how can I make them more theoretically appealing? So, you know, any way you slice it, you might want to get to a place where, in our context, we figure out how to take this nice tractable dynamic Nelson-Siegel model and make it arbitrage-free. Or how to take these nice arbitrage-free Duffy-Kahn style models and how to make them tractable. And the way we're going to do that, we're going to find, it's going to turn out that there's a unique element of the Duffy-Kahn class that has the dynamic Nelson-Siegel factor loadings. And we'll see how we'll figure it out. Okay? So here's how this works. So, you know, you start with an assumption about the short rate, okay? So the instantaneous dynamics of the short rate are affine in some state variables x. That's the top equation there, okay? And then you've got some, you know, dynamics for those state variables given in the second line. So this is a standard, you know, continuous time setup where we've got some state variables evolving with a diffusion. I've made the volatility matrix, the diffusion matrix, sigma there, constant. You could allow for stochastic volatility, and in some recent work that's being done, and so on. But this is kind of the simplest setup. And this is not our setup. I mean, this is not anything new. This is just Duffy-Kahn from a long time ago. And the amazing thing, the beauty of the Duffy-Kahn result is the last equation there. What they show is that in this environment, amazingly, bond yields in equilibrium are also affine functions of those same state variables, x, which is a very convenient, tidy sort of situation. Potentially with a yield adjustment term, that's what that capital pi is at the end there. And they give the formulas of the loadings, b of tau there. Actually, they give formulas for b of tau and pi of tau, the factor loadings and the yield adjustment terms, as solutions to sets of differential equations that they provide. So it's a very tidy, kind of closed form, analytic environment, very, very popular in theory for that reason, but again, not terribly tractable empirically. So here's what we're going to do. We're going to do just what you would guess. We're going to kind of reverse engineer, okay, Duffy-Kahn. I'm going to stick in the Nelson-Siegel factor loadings, okay, for the Duffy-Kahn factor loadings, and work backward and ask whether there's a risk-neutral dynamics. Well, I didn't say it, but those dynamics up at the top there, that's in the risk-neutral measure. We're going to ask whether there's a risk-neutral dynamics. In particular, the key parameters are rho 1, how the shirt rate loads on the factors, and k, the dynamic parameter for the underlying state variables. We're going to ask whether there is a rho 1 and k that support the Nelson-Siegel factor loadings. There needn't be. That's the first thing to notice. There needn't be. It's not at all clear. Okay? It turns out that there is, and it's unique. Okay? So here's how it looks. Just jumping right to it, I'm sparing you the details, but it turns out that if rho 1 has the form there and k is the form there, that is the one and only one set of underlying structural parameters that gives you the Nelson-Siegel factor loadings. And notice how much structure is there in the risk-neutral measure. The rho vector there, remember, is saying, so what's that saying? It's got 2 1s and a 0. So that just says the shirt rate is just the sum of the first 2 factors. That's the 2 1s. And the third factor doesn't come in. It still comes into the dynamics because notice that the K-matrix has a non-zero third row. So the third factor, it's working its way in there, but it's not coming in directly through the rho vector. Look at the K-matrix, lots of zero restrictions, also cross-equation restrictions. It's the same lambda coming into different equations. So there's a lot of structure there. But that's a good thing, from a predictive point of view in general. Other things the same, structure, knowing that a certain, so what this is saying is that theoretical thinking in terms of freedom from arbitrage actually puts more structure than we did before, at least under the risk-neutral measure, on the dynamics. So here it is kind of written out. So that's just the same thing we've looked at, but written out in a fuller way. There's the K-matrix, and you can see the short rate at the top is just the sum of the first 2 factors. Okay, so assembling it all then, I mean, this is just what I said, right? So if we assemble it as a proposition, right, if the short rate is evolving that way, where the risk-neutral factor dynamics are given in that big expression at the bottom, then bond yields are arbitrage-free with the Duffy-Kahn form, where the factor loadings are indeed the Nelson-Siegel factor loadings. So it turns out you can make Nelson-Siegel arbitrage-free. I'm tempted to go into marketing mode and say, that's what gives you the best of all possible worlds, et cetera, et cetera, et cetera. I am quite intrigued by this. There are lots of issues. I haven't shown, by the way, there's the issue of the yield adjustment term. Remember, there's that pi thing as well. I just showed you here the factor loadings, but also you can work, it looks ugly, but you can program this up in MATLAB, and for empirical purposes, once it's programmed, it's very simple. There's the formula for the yield adjustment term. Okay? Now, let me show you how things work when we go back to the data and now do arbitrage-free Nelson-Siegel, okay? From a predictive point of view. Slightly longer and richer data set here. This is more recent work. Notice we're going to take maturities out to 30 years, whereas before we only had them out to 10 years. And of course, well, this says December 2002. In the most recent work, it's beyond that as well. But anyway. Let me say one thing about this maturity. Remember, we used to stop at 10 years. It's going to turn out to be interesting to look at these long maturity things. There's an extension of Nelson-Siegel, not dynamic. It predates the dynamizing of it, but by Svensson, by Lars Svensson. And it is linked to long maturity fit or lack of fit. I'll come back to that, but I want to highlight, notice we're intentionally bringing in some long maturities because I want to check out some long maturity issues. So you already know all these models, but just in terms of nomenclature, DNS, okay, is our mnemonic for dynamic Nelson-Siegel. DNS independent just means we're assuming A and sigma are diagonal, so the dynamics are just stacked univariate dynamics, as we already discussed, okay? AFDNS means arbitrage-free dynamic Nelson-Siegel, the model that we just worked out, okay, where we make it arbitrage-free. So AFDNS independent is arbitrage-free dynamic Nelson-Siegel, where again the relevant matrices are diagonal, so there's no cross-variable interactions. And in the papers we also allow for correlation, and it doesn't help much. That's why I'm not showing it. You know, it's the independent case where all the action always is. But you can dig into that if you're interested. But here's what happens. Okay, so you're used to seeing these pictures by now, right? So remember, if we're below unity, that's when we're doing better than our competitor. But it's no longer DNS relative to a random walk. Now what we're looking at is arbitrage-free DNS relative to regular DNS. I mean, we saw earlier that regular DNS did a lot better than a random walk, at least for medium and long run forecast. So if we're doing better than regular DNS by imposing no arbitrage, then we're doing way better than a random walk. Okay? So the relevant comparison now, though, is imposing versus not imposing freedom from arbitrage. So the RMSE ratio on the vertical axis in these pictures is arbitrage-free DNS relative to regular DNS. And you can see at all horizons, all the dots are below 1. So imposing no arb is actually helping. And you can see as you move rightward to the middle and right subpanels, it helps relatively more. And most strikingly, you see that it's at the longest maturities. For some reason, I don't know why, we do a 20-year maturity, but somehow that dot got left out of these pictures. But it's right where you'd expect it to be. It's higher up than the 30-year dot, but not nearly as high as the 10-year dot, okay? So, like in this picture, if I had that dot, it would be right about there, okay? But you can see that the relative help from imposing, oh, you don't see anything on the, was it there? Yeah, it would be right about there, okay? So then it vanishes. Okay. So there's this interesting phenomenon of, in general, interestingly, imposing no arb helps. I like that from a predictive point of view. That's one of the reasons why I'd wake up at 3 a.m., right? Because it's not just that the theory guys like no arbitrage. It's more that, think of it from a shrinkage point of view. As statisticians, right? I mean, you all know that shrinkage can be a wonderful thing in predictive environments. In fact, from my point of view, it's one of the great unifying ideas in prediction. Good predictors almost always involve shrinkage of some form or another. Now, what's the obvious direction to shrink in this kind of a context? Even if you don't believe or don't want to believe in no arbitrage, still in terms of a shrinkage direction, it's the obvious direction that theory points you in. I mean, and then you go and do it. You can do it because you're a finance person and really believe in no arb, or you can do it from a statistical point of view of just shrinkage, and it's a logical direction to shrink in, even if I don't believe it truly. By the way, this is like I'm actually imposing no arb. A very interesting thing, which I have a student working on, but I don't really have any results yet, is of course to actually do the shrinkage. So you set it up in a Bayesian framework where your prior involves no arbitrage and coax things in that direction without forcing it. Okay, so here I'm actually forcing it. I'm imposing no arb, so it's kind of an extreme shrinkage. But anyway, you can see it always works, but it always helps, but it really helps at the long maturities. Now, let's go back to Svensson for a second. So Svensson, a very smart guy who some time ago, like 15 years ago, did the following. It turns out that, Nelson-Siegel aficionados evidently knew for a long time that when the static Nelson-Siegel that they used to fit in the cross-section, to the extent that it ever had trouble or didn't fit well in certain ways, again, usually it did fit well, but when it had problems, they were almost always involving long maturities. The Nelson-Siegel curve evidently, although it's quite flexible, didn't seem to have enough flexibility to capture long maturity yields. So Svensson in the mid-90s proposed a four-factor generalization of Nelson-Siegel, which of course only has 3 factors, where the nature of that fourth factor is to give it a little more flexibility at long maturities. So notice what we've done here. We haven't gone to a fourth factor or anything like that. This is just good old dynamic Nelson-Siegel, but we've made it arbitrage free. And where does imposing the freedom from arbitrage wind up really giving you the bang? At long maturities. So, you know, it's kind of interesting. We didn't have to go to more factors or anything like that. Just impose no arb, and it seems to patch up this problem. This is just a plot of the yield adjustment term decomposed in certain ways. That's not, let's skip that for now. Since we're talking about Svensson, let me go right to Svensson, okay? So here's the so-called Svensson, okay, 1995 setup. So, right, the top curve there, it's a terrible typo. The epsilon on the right there in the top equation should not have a time subscript on it. Again, Svensson's doing that as a static model. It should be epsilon of tau, just the way it's y of tau on the left. It's a cross-section fit. But notice he's brought in a fourth factor, okay, which is effectively a second curvature factor. We can generalize it, we can dynamize it, of course, in the same old way, which is what that second equation is doing. But here's the interesting point. You can say, let's make this dynamic Nelson-Siegel-Svensson model arbitrage-free. Okay? Do the same thing, you know, do the Duffy-Kahn setup, work backward, figure out the dynamic restriction, the risk-neutral restrictions that make Svensson's dynamized model arbitrage-free. One can prove that there is no parameter configuration that does that. Okay, you'd think it would be a trivial parallel to making Nelson-Siegel arbitrage-free. Nelson-Siegel-Svensson's is a trivial extension of Nelson-Siegel. I should do the same trick. It turns out it's provably impossible to do that. There is no arbitrage-free Nelson-Siegel-Svensson. Which I thought was kind of interesting. What you do get, what does come out of it is that if you add a fifth factor, as we've done there in the bottom, a second slope factor in a way that's similar to Svensson's second curvature factor, then that five-factor model can actually be made arbitrage-free. But it's not clear that there's a need to. Just taking the good old three-factor Nelson-Siegel, making it arbitrage-free, goes a long way toward patching up the long maturity performance, and that was basically all that anybody had ever really complained about in terms of the Nelson-Siegel performance. But there are interesting issues in terms of when you can and when you cannot make these sorts of things arbitrage-free. So, you know, this is just saying in this generalized Svensson model, this five-factor model that we cooked up, what the restriction is that's needed to make it arbitrage-free. I won't torture you with it. Instead, let me just think about the future with you for a minute, and then we can you know, open it up to questions and so on. I mean, some of these things we've mentioned already, of course. What we've done is taken Duffy-Kahn and made it tractable, or taken tractable Nelson-Siegel and made it rigorous in the sense of arbitrage freedom. So nothing really more to say there. But this arbitrage-free Nelson-Siegel really is kind of nice. It is, in some sense, the best of both worlds. And imposing the no arbitrage does seem to help. Now, there are many things you could do in terms of the future. Some of them are starting to be done, and some aren't. Just in terms of a random set of things. I mentioned a minute ago shrinkage as opposed to direct imposition, you know, in the direction of the no arb restrictions. That'd be very interesting. A Bayesian analysis of this model in general would be very interesting. Again, it's all in state space form, so there's a natural kind of Carter cone, you know, structure for generating Markov chains to do posterior draws on all your parameters and so on. So it'll be very, there's enough tractability you can see built into it so that it should be easily feasible. Another thing that I didn't say anything about is stochastic volatility. I know many of you are interested in stochastic volatility, so am I. And you know that asset returns in general and bond yields in particular certainly don't have constant conditional variance. You know, so that might be something you care about. I mean, there's kind of the statistical, in this context, I view the statistical issues as smaller. I mean, certainly if there's heteroskedasticity, if you want to think of it that way, then full estimation efficiency requires that we acknowledge it and take account of it. You know, fine, but these samples are big, and the estimators are still consistent. So, you know, I don't get so worried about that. Now, other statistical issues, though, are much more important. Clearly, if you want to do interval forecasting or whole density forecasting, which can be very important in risk management and many other contexts, taking account of time-varying volatility could be central. Are your intervals getting tight when they should and getting wider when they should? And maybe at different places on the yield curve, different things are happening. Maybe short rates are getting less volatile at the same time as long rates are getting more volatile. You know, to get at all those sorts of issues, you need a model that allows for time-varying volatility. So that could be, that's a statistical issue, but very important. We were just doing point forecasts here, so it really didn't come up. But you might want to go beyond that and look at intervals or densities. And certainly in a Bayesian framework, you're automatically doing, you know, posterior, you know, predictive PDFs. But also from an economic point of view, time-varying volatility can be very important because that should work its way into time-varying risk premia, which has to do with fundamental aspects of the economics and the freedom from arbitrage. You know, that's all been kind of pushed aside here. So I think that would be very interesting to look at. And there are many other things. Many people are working on these sorts of things right now, but I want to focus in the brief remaining time on one issue which I think is really central. And that issue is the following. I mean, to tell you the issue, I have to tell you a little bit about this interesting new paper. Two interesting new papers, one by Greg Duffy, 2009, and one by Ken Singleton and Jocelyn Azou, 2009, listed there at the bottom. What those papers are, especially Singleton's paper, well, actually both of them, they're kind of reactions to the literature that I've just spent, you know, the last hour describing to you. And what they show is that, so what we've done by making Nelson-Siegel arbitrage-free is arrived at this model that's both arbitrage-free and tractable, unlike the earlier vintage Singleton-style models. What Singleton does is he shows, in fact, that this dynamic Nelson-Siegel at which we've arrived is, in fact, just one member of a broader class, a broader subset of Duffy-Kahn that is, of course, arbitrage-free, but also numerically tractable. So what these brand new papers are doing is saying, okay, you've arrived at this model that's empirically tractable and free from arbitrage. It turns out that it's not the only one. Okay, it's one member of this class. So then the question is, okay, is there anything special about it? Given that it's only one member of a broader class that's simultaneously arbitrage-free and tractable, do we want to stay with it, or is it just, you know, no better or no worse than any other of these sorts of things? Well, that's an open question, with a lot of people kind of working on this. In part, I guess my opinion is biased. You know, I want to believe that dynamic Nelson-Siegel is going to stay central, because I've invested some time in it. But, you know, making an attempt to maintain scientific disinterest and try to think about the actual situation, there are interesting results kind of coming out now. In particular, there's this guy named Leo Krippner in New Zealand who's been studying this very hard from approximation theoretic vantage points, sort of like Laguerre polynomials, that I don't completely understand yet, but anyway, Krippner's abstracts say that you know, dynamic, you know, arbitrage-free Nelson-Siegel is in fact very special. And the empirical work that's coming out always seems to lead people to models that are either arbitrage-free Nelson-Siegel or very, very close to it. So, you know, it's much too soon to say anything with any seriousness or any precision. But I think it's an interesting situation in that, you know, all of a sudden you figure out how to make Nelson-Siegel arbitrage-free, and then the next result is, okay, fine, but in fact, there are other models that are also tractable now that are arbitrage-free. And then the Krippner-style result is, yeah, but in fact, Nelson-Siegel is first among equals, perhaps. So it'll be interesting to see how all that unfolds. I don't know what the answer is going to be yet, but there's still a lot to be done. That's all. Thank you.
Two questions. You said a little bit about the uniqueness of these results in this particular setting. So I wonder whether we could maybe go beyond that, making it more flexible. First of all, maybe looking for alternative parametric forms fulfilling the same requirements for arbitrages, or maybe doing it even semi-parametric way. Maybe that's a related question of what to ask, I'm not sure.
I'm well prepared for Wolfgang's semi-parametric question. We'll come.
That is already a little bit semi-parametric. So basically the question, do you have any sense whether we could go beyond that, also fulfilling this arbitrage restriction, which is kind of, yeah,
right.
Strange and
right.
No, should do maybe even better.
Right.
And the second question is, do you have any, did you ever look at how important, so the number of factors. So what is the relative contribution to these out of sample? So in sample we know very well, okay, we're fine.
Good question.
Factors, we're doing very fine, and third factor adds a little bit on that.
Right.
And then, but for the out of sample prediction, I would be interested on the relative contribution of the individual factors.
Sure. Okay, so the first question is, you know, maybe, you know, can we go beyond or away from the Nelson-Siegel and still have these desirable properties? I mean, in part, I mean, that's exactly what the singleton thing is doing, right, that I was just alluding to. So people are starting to look at that. Here's part of the intuition why I'm guessing, though, that when all the smoke clears, the arbitrage-free Nelson-Siegel will still be central. Again, sort of, you know, maybe first among equals. It is the following. Going back a long time, and quite apart from this Nelson-Siegel stuff, people like Jose Schenkman and Litterman, you know, in the late 80s, early 90s. Schenkman-Litterman's a great paper, actually, right? There's been this inescapable recognition that factor structure, or something very close to factor structure, is just, you know, the key element of the data generating process here. And, you know, that's what the Nelson-Siegel or the dynamic Nelson-Siegel sort of gives you. Now, there may be, you know, rotations, but that in terms of fundamental aspects, they're all going to be the same model. So that's not a modeling issue, that's just the way the data is. And it happens that the Nelson-Siegel is built in a way that captures that. So, you know, the answer to your question, I think, is yes, there are variations and so on, but I think most of the ones that are likely to remain empirically maximally relevant are going to need to have this factor structure, and that's sort of where this takes you. In terms of the second question, which was, what's the comparative importance of the three Nelson-Siegel factors in out-of-sample prediction? Well, you know, in my experience, which of course is not all-encompassing, but in my experience, it's like any factor analysis that I ever see, at least in economics or finance, because that's more or less all I ever see. But what always happens, right? The first factor soaks up, you know, 75% of the variation. The second factor gets 22%, and the third gets, you know, 3% or something. You know, that's certainly happening here. You know, sometimes I flip-flop on this, but sometimes I get I sort of say, why don't we throw out the stupid third factor? Another thing is that nobody understands the third factor. The first factor, when you correlate it with macro fundamentals, is very much about inflation and expected inflation, as you would guess. If everybody thinks inflation is going to go up, then all nominal yields should go up at the same time by the same amount to preserve the real yields. And the second factor, theory suggests, and empirically it comes shining through, is all about real economic activity. It moves over the business cycle very clearly. The third factor is much harder to understand in theory. It arguably should be about stochastic volatility. Through some convexity argument, you might imagine that volatility should impact the curvature of the yield curve, but empirically that's much harder to tease out. So anyway, first factor explains a lot more variation than second, and second explains a lot more than third. But you know, we and most people tend to keep all three. But you know, for some purposes, if you made me drop the third, I wouldn't care that much. Yeah.
Frank, thanks a lot for this very interesting introduction into dynamic Nelson-Siegel and how to actually dynamic Nelson-Siegel. But let me start from one of the first slides where you introduced the static Nelson-Siegel. Suppose I do a little experiment, not looking at time structure, just fit at certain time points, static Nelson-Siegel.
Right.
I will observe, as you said, varying betas, but certainly I have to fit this lambda also.
Yeah.
And now if you move from NS to DNS,
yeah.
you actually kept the lambda not time varying. So
right.
I was wondering, of course, it makes
it's a good question.
Easier, much easier. So and I would have done the same way, but I would like to know that you comment a little bit about the dynamics of lambda.
Right. No, that's right. So you want to know about the dynamics of lambda. That's right. See, this is illustration of the old dictum that nothing's impossible for the man who doesn't have to do it himself. It's a completely reasonable question. Let me speak to that a bit. I didn't emphasize this, so I'm sure it wasn't clear at all. But there are ways of thinking about lambda. First of all, what lambda governs, okay? What I'm saying is approximately true. There's a slight issue. But what basically lambda governs is where the loading on the curvature factor achieves its maximum. Now, you know you don't want that to be at an absurdly short maturity. You don't want it to be at an absurdly long maturity. Somewhere in the middle. Reasonable people, of course, could debate where in the middle is. But what we did is just reverse engineered it. We picked that lambda that gives us a maximum on the curvature factor loading at 24 months, 2-year kind of mid-maturity, and froze it there. So it's not as if lambda is being picked in an arbitrary way. There are features of the situation that help you. Now, second, one can of course estimate lambda. Either estimating it under the assumption that it's fixed, but still estimate it as opposed to just setting it as we've done. Or, it'd be trickier, but estimating, allowing for time variation. We played around, actually. Over the years, we've done some of that, certainly not as extensive as we or others might like. But my kind of qualitative assessment of seeing what people have done is that there are a lot of margins to work on. I'm not sure that worrying about lambda is at the top of my list. I could be wrong, but I don't think it's at the top of my list, because people have done it and it doesn't seem to make much difference. Third, and this is linked to the no arbitrage theory, constancy of lambda actually comes out of the no arbitrage theory. If you notice in the Duffy-Kahn style model that we wrote down, not only does it impose restrictions on the risk-neutral density, but it's a fixed lambda that's showing up in those risk-neutral dynamics. So, my view is that the issues you raise are completely worth raising, but I don't wake up at 3 a.m. on those. They're worth raising, but I'm not sure that they're at the top of my list. Yeah. Yeah. Right.
When you go from, say, objective measure to geometric Brownian motion,
yes. Yes.
You have this Yazani transmission, you can see and interpret this market price of risk, which is
yeah.
And quantity that must also occur somewhere here. And I would like to know whether you would be interested in what you thought about bridging to the literature of financial behavior or behavioral finance, I should say, because what you observe is in subsequent or moving in time towards this design transmission, you will see actually time varying market price of risk.
Yes.
Again, this was one of the first comments, can relate to macroeconomic indicators.
Yes.
And so you should, I think it was your DeFi or DeFi or DT or so, maybe it was transmission, but at least identify it, it would be nice if you could comment on that.
Sure.
I'm thinking more like
Sure, there's actually a funny story in there too. First of all, I would say that the issue you just raised there is very much at the top of my list, or should be at the top of anyone's list. I didn't mention it in wrapping up, but it's definitely something we've thought about. So here's something that I didn't stress. I actually didn't mention it in the talk, but it's exactly on the issue that Professor Herlet just raised, which is, what's the nature of the transformation from the risk-neutral to the physical world here? Well, it turns out that imposition of no arbitrage in this environment, the arbitrage-free DNS as opposed to regular DNS, the only restriction it puts on the physical measure, remember it put a lot of restrictions on the risk-neutral measure. We saw those zeros and cross-equation constraints and so on. But the only restriction put on the physical measure, which is the one, of course, that's ultimately relevant for prediction, is through this yield adjustment term. It's like in other words, it's a function of maturity, only time. So, I said that incorrectly. It's a function only of maturity, not time. So it's like a constant adjustment. Now, that term, though, is not the market price of risk. You said it exactly correctly, but that term is related to the market price of risk. We should be able to, we could figure out, the implied market price of risk and look at it and see if it's linked to the business cycle or whatever. We have not done that yet, and I want to do it. It's funny because I told you at the beginning, and maybe somebody here is doing it. Yeah, I told you at the beginning that Jens Christensen is this great guy at the San Francisco Fed who we've been working with, and more than once, Glenn and I said to Jens, we should plot out the market price of risk, and he goes ballistic. He just doesn't like. I can't understand why, but he doesn't think that's a good thing to do. And sort of smoke starts coming out of his ears, and without his saying it, he effectively says to me, Frank, only a moron would want to do that. You're barking up the wrong tree. Stop asking me about that. So we go away and stop asking him. But we keep coming back and back, and I agree entirely. You'd want to look at the market price of risk and see how it's time varying, and you might want to see if it's time varying in strange ways, because the fact that the physical world restriction involves only this yield adjustment term that's constant over time, which is very special, suggests that there might be some parallel special things going on with the nature of time variation in the market price of risk. I think that should be done, and it's embarrassing that we haven't done it. So I think it's very good. Yeah.
Frank, I really like your design of talk. I just and I was also asking your question that you already answered at the last piece. So instead of asking theoretical questions, we asking practical questions.
Yeah.
So you were forecasting, let's say, 6 months ahead yield curve and 12 months ahead yield curve. And I recall you said that you were doing like regression 6 months ahead, or you are using dynamic.
Yeah.
I don't know which one you're choosing.
Oh, like are we? Yeah. Okay. So, right, we're using AR1 dynamics. So if I'm understanding your question directly, the question is, our data is monthly. So the question is, do we take a monthly AR1 coefficient and raise it to the 12th power, or do we regress xt on xt minus 12? We do the latter.
The last one.
Yeah.
And the second related to this question is your conclusion. How much depends on the method you're using?
I'm sorry. Say that again.
Depends on the Zoom method you're using. Suppose you and I apply a different model, a dynamic model, arbitrage-free sequel model. using two different methods rather than 6 different methods.
What different methods do you have in mind?
One, let's say using AR1, the other
Oh, sure.
using 12 model, or the other one.
Oh, yeah. Oh, sure. Sure, no, we've played around with things like that a lot. Again, sort of a priori, since the factors are close to the principal components, you'd think that some orthogonal things would matter, but again, that doesn't mean they're going to be AR1s. So in terms of our use of orthogonal AR1s, there's the orthogonal part and there's the AR1 part, and you're asking about the AR1 part. So we've also done full, vector autoregressive systems. We've brought in different amounts of economics, like using Campbell-Schiller type regressions, using Fama, Bliss, Cochran-Piazzesi type, forward rate regressions. These vector autoregressions I just mentioned, we've done, with and without co-integration, so error correction models with one co-integrating vector or two or three. So we've played around a lot. So in part, our use of the simple AR1 structure was just before we looked at the data, we just sort of said, look, let's just keep it clean, and we'll view our results as some lower bound on what a more sophisticated person might be able to achieve. But in addition, after playing around with a lot of other models, certainly not an certainly not an exhaustive set of models, but a fair number of other models, it turns out that the AR1 seems to be as good as anything else. So from both sides, we just sort of stayed there. But a sophisticated modeler like you, I don't doubt might be able to come up with something seriously, something even better. So ultimately, I would just say, we basically just picked the AR1. We're not claiming that AR1 is necessarily the best, but and anyway, what we're saying is, look, even just for a simple AR1, look how much it works.